The uniform 30 kg bar with end rollers is supported by the horizontal and vertical surfaces and the wire AC. We are tasked to find the tension in the wire, the reaction at A, and the moment at B. So to solve this problem, let's draw our free body diagram. So we have a rod with end rollers, therefore it experiences a force that is normal to the surface. Let's call this reaction A. And this one is reaction at B. And we have a tensile force due to the cable AC that will induce a force going in this direction. So the distance from, or the angle between the rod and the horizontal surface, since we are given the length of 1.2 vertical and the 1.6 horizontal, so that's basically tangent of theta equal to the opposite side of 1.2 divided by the adjacent side of 1.6. So theta, by using the arctangent function, that is equal to 36.87 degrees. And then for this angle right here, let's call this beta. So we are given the distance of 0.6 on this side and 1.12. Therefore, the sum of this vertical distance here is 1.8 meters. So considering this right triangle with an opposite side of 1.8 and an adjacent side of 1.6, therefore the total angle is equal to the arctangent function of 1.8 over 1.6 to get this angle, total angle of 48.36 degrees. And to get this angle beta, we subtract this to the angle between this horizontal distance and by the rod. So minus 36.87, that is equal to 11.49 degrees or 11.5. That is this angle here. So we can, no wait, we have the weight of the bar, since it has a mass of 30 kilograms that is located by the centroid. So the weight, that is equal to the mass of the bar times the gravitational acceleration of 9.81. So that is equal to 30 times 9.81, which is equal to 294.3 newtons. Now we can take summation moment at point A, so as to neglect the tensile force and the reaction A, so we can solve for B. So by taking summation moment at point A equal to 0, considering counterclockwise to be positive, we have reaction B times the moment arm distance of 1.2 meters, which is this distance from here to here. Since it is going in the counterclockwise direction, therefore it's positive. And then we have the force, or the force due to its own weight of 294.3 newtons that would induce a clockwise moment, so it's negative, times the moment arm distance of 1.6 divided by 2, since the centroid is located halfway between the distance from A to B. So that is equal to 1.6 meters divided by 2, equal to 0. Now we can solve for the reaction at B by using our calculator. So we let x be our RB times 1.2 minus 294.3 times 1.6 divided by 2 equal to 0. We get our reaction at B, that is equal to 196.2 newtons. Next, we proceed solving for the reaction at, let's start with tension T, because we can take summation force horizontal equal to 0, and since we are given for the reaction RB, we can solve for the tensile force T by taking summation force horizontal. So we have negative RB since it is going to the left, and then plus the horizontal component of the tensile force T, that is T times the cosine of 11.5 degrees plus 36.87 degrees. That is equal to 0. Now we can solve for t using our calculator. We have negative 186.2 plus t cosine of 11.5 plus 36.87 equal to 0. Shape solving, we get t equal to 295.34 newtons. And then lastly, we will solve for the reaction at A by taking summation force vertical equal to 0. So we have the reaction at A going upwards, so it's positive, plus the tensile force T, and it has a component acting vertical, so we take the sine of the tensile force T, so that's T times sine of 11.50 degrees plus 36.87 degrees. And then a force due to its own weight that's going downwards, so we subtract this by 294.3 newtons, all equal to 0. So we have T that is equal to 295.34. We can solve for the reaction at A. So we have RA plus the tensile force T that we have solved a while ago. That's 295.34 times sine of 11.5 plus 36.87 degrees minus 294.3 equal to 0. Shape solving, we get the reaction at A equal to 73.55 newtons. So we have our final answer for number 1, that is 295.34, and for number 2, that is 73.55, and for number 3, the moment at B. So we take summation moment at point B, and then that is equal to the moment due to the reaction at A times the moment arm distance of 1.6, and assuming that counterclockwise to be positive, so this is negative since it is going in the clockwise direction. And then we have the tensile force T that has a vertical and horizontal component, so we take that into consideration. So let's start with the vertical component, that is negative T, since that it induces a clockwise moment, times sine of 11.5 plus 36.87 degrees. Let me erase this first. So we have negative RA times 1.6 minus the clockwise moment due to the vertical component of the tensile force, that is T sine of 11.5 plus 36.87 times the moment arm distance of 1.6. And then due to the horizontal component, that would induce a counterclockwise moment, so we add this by T cosine of 11.5 plus 36.87 times the moment arm distance of 1.2. Now we can solve for the moment at B. So we have negative RA of 73.55 times 1.6 minus T of 295.34 sine of 11.5 plus 36.87 times 1.6 plus T of 295.34 cosine of 11.5 plus 87 times 1.2, and we get our moment at B, that is equal to negative 235.44. Since it's negative, therefore the moment at B must be in the clockwise direction. Since we're assuming counterclockwise to be positive, since we get a negative value, therefore the moment at B must be clockwise. This is in Newton meters. So that is the final answer for number 3.